Today we begin a new unit on gas chemistry, and the lesson that we focus on today focuses on the behavior of gases and some general properties that they exhibit. Let's first start by discussing the major differences between the three states of matter and their motion. So you should know already that in any kind of solid substance, the atoms are constantly moving. We know this. This is particle theory stuff. All of our atoms are in constant motion, just that the motion is different depending on the state. So if we have a solid, the motion is vibrational. The little atoms go back and forth, and they'll speed up or slow down with temperature, but they just move side to side slightly. In liquids, they have the same vibrational motion, and they also have rotational. So rotational implying that they move in a circular form, if this is my atom, and they move in a circular shape. Sometimes you notice this with liquids when you've heated them or you're mixing things or you add food coloring to it. You can actually kind of see the molecules move around in a circular fashion. But gases are very different. Gases only have one type of motion that is called translational motion, and this means straight line motion. So they travel in a straight line until they collide with something in their path. This is usually an object or a ceiling or a wall. And then with whatever angle they hit that object at, they will deflect and they will carry on in the same angle and keep on moving in a straight line until they hit another object. So out of the three states of matter, which one has specific volumes? Well, we know that solids, you can measure their volumes. There's many different formulas to measure regular solids. Irregular solids can be measured usually with water displacement. And we know that liquids also have a specific volume. 100 mils is 100 mils. Which has a specific shape? Well, only solids have a specific shape because we know that liquids, if you have 100 mils, you could put that in a tall graduated cylinder. You could put that in a big beaker, a small beaker. Their shape can change. And gases also have different shapes, different volumes, depending on the container they are held in. Here's a visual of your three states of matter in a way that the atoms interact or behave. You can see that the solids are usually arranged in some sort of regular pattern. Liquids are held together, not as strongly as solids, which have usually ionic forces of attraction or the covalent strong hydrogen bonds. In liquids, again, depending on the intermolecular forces in between the type of substance, the arrangement will be, tighter or a little bit looser depending on the attractions. And most gases are non-polar, so they're only held together with dispersion forces, which are very weak. And as a result, they move away from each other, and there's lots of spaces between gas atoms. The fourth state of matter is plasma. It's here in this image. We do not really comment on plasma in any chemistry class in high school, simply because it is a type of matter that exists out in space. So one of the unique things about gases, and there are many, is the fact that because they have so much space in between them, we can compress them, okay? So we can force these gas molecules to decrease their volume if we apply pressure, okay? So we have to apply some sort of force to them. And as it says there, a gas can be squeezed into a small space. And the reason that you can is because there are all kinds of spaces between these particles. And so you can shove a lot of them into a small space, far more than you could with a liquid or a solid. So there is a kinetic molecular theory or kinetic molecular model of gases that we'll just touch on here a little bit. And one of the statements of this theory is that gas molecules completely fill up their containers. And this is true. If you put 100 gas molecules into a glass jar with a lid, depending on the size of that jar, if it was a 250 ml jar or a 500 ml jar, those gas molecules would just expand and they'd fill up that container. And then we would say that the volume of the gas was based on the volume of the container you put it in. So knowing this, are gases in continuous motion? Absolutely they are. Everything is. But gases, again, have that translational motion that they just keep moving in a straight line until they fill up their container. The second idea is that gas molecules have low density. Remember that density is the relationship between mass divided by, not molar mass, mass divided by volume. And then as a result, they are easy to compress. So if we know that they're easy to compress, are gas molecules far apart from each other? Yes, they are. And we know why. They have very weak intermolecular forces. They are only attracted to each other through dispersion forces, which at room temperature, usually there's enough energy in the room, can separate these molecules and send them far apart from each other. Number 3 says gas molecules are easy to expand, and this kind of goes with number 2. So it says, are gas molecules strongly attracted to each other? No, they're not. And we just touched on that because of dispersion forces. They are not attracted to each other very well at all, and so they will get as far away from each other as possible. One of the most important concepts related to gases is this concept of pressure. With gases, we relate almost every type of gas back to its pressure. And you have to understand what this concept means. Pressure is the force per unit area that gas molecules exert as they collide with objects in their path. So I'm showing you here some samples of gas molecules with arrows moving around in translational motion. And here's a great one right here showing, the angle with which it hits. It'll deflect with the same angle away from that container wall. And every time they collide with the sides of those containers, they exert a force. So if you don't have a lot of gas molecules, they don't exert a lot of force. If you have a lot of gas molecules, then it's going to exert a lot of force. Our atmospheric pressure, because we know that above the Earth, we have all these gas molecules making up our atmosphere, is the equivalent of 101.325 kilopascals. That's what that unit stands for. And this doesn't really mean much to us. We understand this is a pressure unit. We understand now this is a force. But, how much of a force is this? Well, I have heard a few times that this would be the equivalent of 2 or 3 cars, resting on top of your head. Okay, now this is a lot of force. And if we had 2 or 3 cars resting on top of our head, we would die. Okay, we would be crushed. We don't feel that immense force for 2 reasons. One is that we were born into this atmosphere, so we became used to it right away. And secondly, the force doesn't just come at the top of your head. It is distributed all over your body. And you also breathe in and out, with gases to try to combat that force as well. So it doesn't really affect us, but we certainly can notice changes in pressure and altitude when we fly, even if you just go up, mountain climbing up a high mountain. Not that we all do that, but people have to get used to that change in pressure. Kilopascals is the most commonly used unit of pressure, but we need to be aware of other units. So these are equivalencies that you must know. Okay, you must know these. And that is that 101.3 kilopascals is the equivalent of 1 atmosphere, which is also the equivalent of 760 torr, and also 760 millimeters of mercury. Millimeters of mercury is the unit that is used when we take our blood pressure. 760 torr, I'll admit torr is probably the least used out of the 4 of those, but torr is short form for Torricelli, who was an Italian chemist who came up with the idea of standard pressure. So this is why they give him some credit and some honor here. I want you to stop the video right now and then go over to Google Classroom and watch this video that I have loaded for you. So although pressure is a very common way to describe a gas, there are 4 variables that we do use to describe a gas and its behavior and its properties. Pressure is the most common, and it is typically measured in kilopascals, but as we saw, there's other equivalencies for the unit of pressure. We also can describe a gas by its volume, and typically we measure that in liters. We also will talk about a gas in terms of its temperature, because we know temperature really has an effect on gas molecules. It'll cause them to move around a lot faster or a lot slower, depending on whether you increase or decrease the temperature. In gas chemistry, we use a new temperature scale called kelvins, and we'll get to that in a future lesson, but we need to be aware of that is the temperature unit that we use. It's called kelvins. And then where would we be in chemistry without our good old mole? So if we are talking about the amount of a gas, we would measure that in numbers of moles. Let's go through each variable and comment on how it affects gases. So the amount of a gas is kind of obvious. If you add extra gas molecules to a container that is enclosed, okay, and that the gas molecules can't escape, then you are going to notice that the number of collisions between gas particles and also between their container as well, okay, so both of them, is going to increase. So you see here, there's a container that has some gas molecules. You'll notice the pressure right here. And then you'll notice over here, we have more gas molecules, and that pressure has gone up. That makes perfect sense. You're going to have more gas molecules colliding with the sides of your container, more forces being applied to the sides of your container, and your pressure is going to go up. This is what we call a direct relationship. So if we increase the amount of a gas, you're going to increase the pressure. And it's so direct that if you double the amount of gas, your pressure should double. If you decrease the amount by half, your pressure should decrease by half. Here's a common application of gases in that we use an aerosol can probably frequently throughout our day-to-day lives. So how do they work? Inside the can, you have your contents. So I'm going to, refer to, I don't know, like cooking spray, right? That we use, Pam or, the Costco brand that you would spray on a baking pan or sheet or something like that in place of actual oil. And the way that this works is you have this nozzle here with a long tube that is open at the end so that the contents can go out. So whether that, again, the contents is cooking spray or spray paint or hairspray, whatever it is. But in order to get the contents out, you have a gas inside that is at high pressure. And one of the key things to know about gases is that gases want to move from high to low pressure. So the pressure inside that can is higher than atmospheric pressure outside. And so those contents want to get out into lower pressure. And what it does is it forces the contents of your can out of there. Okay, so this is why this little nozzle at the end is open. And that's how aerosol cans work. Now, the problem is if you take that aerosol can and you turn it upside down, you're going to see what's going to happen here. Your contents here are going to go up and the gases are going to come to the bottom if you invert this. Okay. And then what will happen is your gases are going to go out this nozzle and out into the atmosphere, and you lose all of this gas that is called a propellant and needed in order to get the contents out. So this is why you got to be careful here when you use aerosol cans that you don't tip them upside down. Now, as the contents decrease, okay, so as this contents right here, as they decrease, your gases are going to expand more and more to take up more volume, and the pressure will decrease on them slightly. So you might notice that towards the end of an aerosol can that the contents don't come out with as much gusto, simply because the gas propellant that's in there is operating now under a slightly lower pressure due to the increase in volume. So this is a good segue into talking about gases and volume. So if you have a volume of a gas, it will exert a certain pressure on it. And if you change that volume in any way, the pressure will go up or down. So if the volume is reduced, now what will happen, you do not have as far for our gas molecules to travel to hit the sides of the container. And because they don't have as far to go, they're going to apply more force more often. Your pressure is going to increase. If you increase the size of your container, you increase your volume, now your gas particles have way farther to travel in order to exert a force on the sides of that container. Because they won't exert as much force and over a given amount of time, then the pressure is going to decrease. And because we're seeing now a change, right? So if the volume is increased, the pressure is decreased and vice versa, we say that this is now inversely related, or we can say that this is an indirect relationship. So when one variable increases, the other one will decrease. And they will increase and decrease directly in terms of doubling, tripling, quadrupling, that kind of thing. Lastly, we want to comment on temperature. So we know that temperature causes molecules or atoms to move faster, and there's no difference here with gases. So if the temperature is increased, the particles are going to move faster, and as a result, they're going to exert more of a force on the sides of their container because they're colliding that much frequently, and they're going to increase the pressure as well. This is a direct relationship. So again, as temperature increases, the pressure is going to increase, or conversely, if you decrease the temperature, the pressure is going to decrease. Your particles are going to move slower. They're not going to hit the sides of the container as often. Here are some excellent questions for you to try that you'll see in your booklet. Give those a go and come and see me if you have any questions.